for
once. Do it once. Show the rate of attraction once.
Rick,
Have a
just
prediction.
once.
Show the attraction. Showing it, doing what you predicted. In reality.
The thing that makes me laugh is like
I'm waiting.
If you think mass attracts mass, right? How can you account for, say, like an aeroplane going over, and that's not going to ruin your, or cars going past your house? You know, will these masses not attract or ruin the experiment?
No.
Yeah, I mean, the thing about it,
never mind.
Kind of like on tapping onto part of what Riggs was saying before. The thing about it is that you're not isolating anything. So that's why you're only observing movement. And movement, we could talk about what's causing that. So if we have a device and there's movement happening, like the way I described it from my viewpoint, that's one explanation. From there's multiple different explanations as to what's causing that. BioDual is choosing to say that mass is attracting mass. The thing is that we could talk about all kinds of different possibilities as to why it's happening. I would say there is a truth as to why it's happening, but at the end of the day, you haven't isolated anything in order to detect anything, which is what Riggs was, I felt what I was getting from what Riggs was saying. You haven't actually isolated anything, and you're essentially pretending like you are, which is what's strange.
Of course, these things have been, accounted for. And that's why we would bring up scientific papers in which they are using higher technical equipment. Of course, me funding it with my own money in my garage, I'm not going to have state-of-the-art equipment in which I can make the most.
And you're not going to prove shit either.
Fair enough on that. Can you now understand why we don't have a complete model of the entire planet?
I can't understand.
Jill, where's your fucking model, bro? Give me the whole complete model. It's been 6 years.
At some
there's two different conversations going on, right? And that's why Bio's finding it hard to answer. Look, here's the thing. Gio's basically saying that he gets it. The experiment should do in Bio. It does show that the masses are causing something to move, but he's saying that, hey, I get it. The experiment shows that, but he's after the reason for it showing it. And the other people in the room are trying to come up with reasons why, the experiment is bad. There's two completely different conversations going on. Gio's basically trying to say, hey, if it's not gravity, what else could it be causing this? And everybody else is coming up with reasons why the experiment is bunk.
Right, do you have a problem with that?
Well, yeah, can we stick to one shit and fucking get to the bottom of it instead of talking about 12 different things at once?
No, I think that's a good recap. I think both of those things were happening. I think it was good. We were interweaving both of those components because, I mean, that is true, though.
The point is that we're postulating this argument when we're trying to tell you there isn't one, that your shit sucks. So all the flat earthers are allowing this conversation to take place when we already know this is bullshit.
Yeah, but have you guys ever?
Well, of course, but we're trying to get them
maybe
to come to that.
No, I'm trying to let them know that this isn't something that's going back and forth. Like, this is the fucking conclusion. You guys haven't proven anything. You've made an association.
How could you come to the conclusion when the thing that
you're arguing?
I just
explained why.
I know that, but the thing is, talking over me is not going to make you understand it better. I don't think that you understand the argument that you're even making about electromagnetism being stronger than gravity.
That you don't have instruments sensitive enough to detect the amount of influence that you guys are actually trying to
postulate. We obviously do. The problem is that you're assuming that the ratio. I'm
assuming you guys haven't done it at all because that's what I heard.
Yeah. You're assuming that the ratio between which force is stronger means that because it's this much weaker, it's going to take this impossible mechanism to measure it. When they say it's that much weaker, they mean compared to the things that you're using or that are used to create this force. And in the case of electromagnetism, it's charge. In the case of gravity, it's mass. And so there's many cases in which the amount of mass is enough to overcome.
How do you remove that is that much stronger than gravity?
It's that's my point. Is that one argument or that just
I'm
saying
gonna make
that
this crystal clear for the room.
Understand what it means. You have to understand what's meant by that argument.
I'm gonna make this very clear for the whole room, Coach Show. I agree with you.
It's not that it's too weak to be able
but
to
you're
measure.
doing a bad job at explaining.
It's not that it's too weak to be able to measure. It's
No,
that the mass.
I agree
It's
with
the
you.
mass times constant. It can make is what that is how that force is measured. Just like the charge times the constant is how electromagnetism is measured.
I'm going to
But there's
help
many
the whole
cases
room
which
understand because they're not hearing you right now.
the mass is enough. If the mass is enough to create a big enough force, you can easily measure it. And the Cavendish is a good example of having enough mass to measure it. So I mean, it's not impossible to measure. It's easy to measure.
All right.
It's
So what Coach Show is trying to say is that in a game of tug of war, you tie the rope to a tank on one side, and on the other side you have, I don't know, 50 football players, and at the end of that rope is an ant. He's saying that, you know what, we actually have instruments dependable enough to tell the influence of that ant on that other side of the rope.
That is nothing close to what I'm saying. And anytime I need somebody to incorrectly interpret what I'm saying and explain it to other people, I'll get someone to do that. Otherwise, I'll just explain what I mean, okay? Because that's not all, it's not in any kind of way what I mean at all. What's meant is that the two different, take the Coulomb's law. You have two charges times the Coulomb's constant divided by the distance between them squared. Okay, that's how you get that force. Gravitational force, you take the two masses times the gravitational constant divided by the distance squared. Now, the difference between those two numbers is that the gravitational constant is extremely small. So that force can be, the masses need to be big, need to be a lot larger than the charges need to be in order to create an effect that's visible. But there's many cases in which the gravitational force created is going to be much larger than the magnetic force, because the masses are going to be larger than the charges. So it's very easy to measure if you create something big enough to be able to measure. If you have big enough masses, you can measure it easily.
We're all waiting.
I couldn't hear what you were saying. I mean, I was in the middle of talking, so I didn't know what you were saying. But yeah, it's a very simple thing to measure. It's not so weak that you can't measure it. Use the correct amount of mass so that
I'm saying it is.
Yeah, but I know, but that's because you don't know what you're saying. You don't even know what you're arguing. Like that argument is not really it's not a valid argument.
Dude, you're basically saying that you can measure the secret ingredient in a can of Coke. All right, man.
Yeah, it doesn't mean much unless
I believe you.
Unless you have a sufficiently low amount of charge, low amount of mass and a high amount of charge. But you can make the mass bigger than the amount of charge, in which case it's actually not weaker. It's only weaker in a general sense. But there's many cases in which gravity is actually much stronger than the electromagnetic force in specific cases.
I posted a paper in which in two independent ways, they make high precision measurements, and they do account for a number of things. Feel free to look through it, and Control F magnetism if you want, or magnets. These things are accounted for when you're actually doing these high precision measurements. You can run the experiment just for cause and effect. You could do that just for it, and you're not making measurements. But as far as the precise measurements that you do want, this is done all the time, and this is just one method. 2018, further lowering the or becoming to a more precise measurement by a number of different ways.
Okay, does anyone think that they overcame my point?
I'm not sure what your point was.
No. The fact that gravity is much weaker.
Right. I think the better analogy, if we want to continue with this tug of war thing, would be essentially that you do have a tank, and then you have 40,000 people on the other side, and the flag in the middle isn't moving at all. So you know that the ratio between 40,000 and of something and the one of something would be equal in that instance.
I don't know if anyone's brought this up, Virgil, but Rick, you're actually invoking the wrong force. It's the strong nuclear force that holds atoms together, not the electromagnetic force. That's one of the other four fundamental forces.
Oh no, we're not talking about
Either
that.
way.
Cool.
We're-
Okay, no worries.
We're talking
Yes.
about the
I mean,
Cavendish.
I appreciate the correction, but it still follows the same logic. Like the arguments still exist. Gravity is so weak. If you're actually going to put something, an apparatus together to demonstrate this attraction, then it should follow through with all the expected rates and types of attraction. Like it should be very observable.
No, gravity is not that weak in the sense that it's proportional to the
Well,
mass.
then you guys should have
Let me
consistent
finish.
results. Right? You should have
You're
tons
talking
of
over
these.
everybody. Just let me finish a sentence. So the gravity can be weak if the mass is small, and the gravity can be very, very strong if the mass is large. Do you understand that it's proportional to the mass? That's one of the principles of gravity.
Me and Zanuck actually had this argument before. It's one of the things we disagreed about
Normally, to
before.
have more mass, you'd have to have more matter, which would be more electrostatic.
Charge. No, not always.
No, the problem you've got with that is the strong nuclear force or the electromagnetic force, whichever one you want to invoke, works upon a principle of attraction and repulsion. Both actually work because it's both based on charge. Not that we know why anything has a charge, by the way. So that's another fundamental thing that we don't understand why. So gravity, you've got the amount of mass, and that's proportional to the mass that you have around you. So again, not really a problem. I don't see where the argument is here.
Yeah, but that's the point, is that the argument is a general. The argument only exists in a general sense, that generally one force is greater than the other force. But just as Zanuck has just said, and also as I said against Zanuck at one point in the past, we had this argument. Generally, those two things, one is stronger than the other. But in specific cases, there can be so many specific cases in which the amount of mass is enough to create a gravitational force, which is going to be much greater than any kind of combination of the charges, especially whenever you need either opposing charges or like charges or charges at all.
You guys are giving me a headache.
You're going to need charges at all to create any kind of force. If there's no charge at all, like a neutron star, for example, there's a lot more gravitational force there than there is any kind of electromagnetic force, because there's no charge.
And the other thing I bear in mind, Rig, is the distance that these things operate on. So the strong nuclear force is really, really strong, stronger than the electromagnetic force by a long way, by the way, but only at very, very small distances.
Why are we talking about? Never mind.
These magnetic forces, they can prove to be decaying.
I just don't think you guys could pull it off.
Some of these electromagnetic forces can be decaying with the square of the distance, not the cube of the distance.
Yeah.
And so that's key right there.
And then you got the
always
amount
following square of the distance. But
And then you got the amount of energy that's required to generate that force, and that's the other problem. So mass is its proportional representation, and again, with things like the electromagnetic force, for me to double the value of a field or the effectiveness of a field or the range of a field, I have to put a lot more energy in, a lot more. I think it's again, it's that inverse square increase. No, it's an exponential increase.
Yeah, again, we're talking about whether or not BioJoule's results for Cavendish was caused by magnetism. And now for some reason we're talking about something completely different. BioJoule's already said that, by basically doing the experiment in the way he did, he's got compensated controls to negate electromagnetism as being the reason for this.
Are we back to dielectric materials?
Or you could just measure. You could, if you have enough instruments there, you're measuring the pressure, the whatever else, the electromagnetic force. You can measure all that stuff to see if it's influencing anything. And I think that in his case, he was.
I think it's just an excuse to hand wave away results you don't like. Sorry, Rick.
I kind of like Geo's perspective on it. Is he's accepted the results, and he's trying to come up with an explanation for why it's shown. I mean, basically, what Geo's saying is, okay, I accept it's not magnets causing this. It is the mass, which is the fundamental thing that's causing this, but he's saying it's the ether that's playing part with the mass instead of gravity.
Geo and Lemon are they're both tied at the number one Flurf position, at the capabilities of being able to come up with arguments when I didn't think there was one. So I gotta give the both credit for that.
If you call me a Flurf again, if you call me a Flurf again, you're banned for life.
Well, Fleur, you know what I mean.
I like exploring. I like exploring Geo side of it, right?
My
You know what I mean, man. I'm giving you the number one spot, dude.
Well, what I was
sorry, go.
Branch said, okay, well, thanks. Okay, Gosho. But okay,
I mean, no
but
offense.
yeah,
I'm giving you credit, my man. Because Lemon, I'm especially impressed by. Because there's arguments I've had that I thought nobody can have an argument against it, and Lemon has actually I wouldn't call it a sound argument, but an argument that at least has merit and is not just made up on the spot. Yeah, exactly. It's coherent, and actually it does make some sense, and it actually is a rebuttal. I'm like, wow, I didn't think there was one.
Right, it's a better rebuttal than just throwing out random things out, debunking the whole. It's better than just throwing out bullshit. In other words,
just real quick, Branch, to what you said though, because the way you described my position, I mean, I hear that you were just kind of trying to, share it, but I guess I didn't fully feel like I align with what you said. Although it's cool that you said that. But what I'm not saying that it's just electrostatic fields necessarily. In the same way that you could just measure. I'm not saying it's like necessarily static, like the way you can get a balloon to stick to your head. What I'm referring to is the actual field that the matter exists within, like that the matter itself, whatever we call matter, that has its own electrostatic potential. And so that potential is going to be unique to whatever that matter is. So if it's metal, it'll have a particular type of potential. If it's paper or plastic, different things are going to have different components of that. And then the way that interacts within the actual system of the actual ether, it's the fields essentially that are moving the matter. The fields are what exists before the matter. Yeah.
The interesting thing though, Gio, is what you're saying is actually, there's two different ways of thinking about gravity, right? One is, there's two masses attracting each other. Another way of thinking of gravity is the bending of space-time, right? What you're describing is actually pretty similar to that notion of gravity, which is actually bending space-time. But the way you're expressing it is slightly differently.
Well, I think gravity, a rose by any other name is still a rose, and it's the observations that we have, stuff falling to Earth, geodet moving through space, the fact that we can see behind stuff in the right conditions, all these kind of things which sort of comport to the explanations that we have. An incomplete explanation.
It's almost similar a little bit to like in water, you have things in water, right? Like fish or little pieces of dirt that are floating around in water. Well, if there's a movement of the water, it's going to move the little pebbles, like if you're dropping pebbles in water, if there's and in the same way, like this medium that we're in, it's not water, but it's similar in the way that we are actually enveloped in a medium, and the movement of that medium is going to cause movement of what we call matter or mass.
Well, but would you agree that we have less understanding of what ether is to the explanation that sort of supports the observations that we call gravity? It seems to be a weaker argument with less to it than what we already have. So I'm trying to work out where the efficacy is.
Okay, I don't quite know what your definition of ether is in that scenario, but
I want to use yours.
I think it's all interconnected. The reason things fall towards the earth, the reason pendulums precess, the reason Cavendishes wiggle, the reason weather happens, it's all interconnected within the same system, which is why some of these theories, quote unquote, on gravity, they have some truth in it because, what you could call gravity is a very real thing. It's just the interpretation and the model that they pull from it that I don't agree with.
So, Gio, super interesting question here, right? Say if somebody did this experiment, right? Just what would your explanation on this be, right? If they did three of the same experiment, they basically set up a Cavendish and a pendulum side by side, and they did it on the northern hemisphere, on the equator, and the southern hemisphere. Now, the three Cavendishes all have the same exact results. The three pendulums, however, the one in the northern hemisphere, it basically changes direction clockwise. In the equator, it doesn't change direction at all, and down in the southern hemisphere, it goes anti-clockwise. What would your reasoning for the ether causing that type of behavior be?
Good question.
I was really hoping it was going to be a crap question, Branch, so I could have been slightly sarcastic at this time of the morning. You've upset me. Good question.
Well, before Gio, or I guess if Gio comes in, I'll stop. But I was gonna say your question or comment was, I think, good. Also address because I asked earlier today as well that it's funny that they criticize that we have two gravities, Newton's and Einstein's. They criticize it like it's a really horrible thing and blah blah blah. And then they have an infinite amount of unique ideas of ether. Basically each person has their own idea of what ether is. And that's not a problem at all. I don't know, but yeah,
Well,
I know Branch is waiting for Gio.
Well, it is for some of us. We've already, a few of us have already said about that. That's why I put them in the same basket.
Yeah, I mean, for me, all I'm looking for is a consistent standard of evidence used to evaluate stuff. And that's one, I think, for Flat Earth, I think that's one of the majorly big problems. I mean, I'm quite methodological, I'm quite process orientated, what I call that, bump guy. I go through my process.
I hear you do a lot of math, yeah.
I do no math.
Well, you're saying you okay?
No, Branch had a question for you, though, G. I don't want to take away from him. I just I was only saying something because I don't know if you were coming back. Yeah, Gio, you're making my Cavendish wiggle right now, dude.
Oh my god!
I thought it was funny you said that. It makes the Cavendish wiggle.
Branch has been on point. He's had a very clear understanding of the conversation. He's been able to articulate what's going wrong and how people are going off track. And he's been able to bring it back to the point. I reckon Branch should be a mod. That was really well done.
I wish Branch was paying me to lobby for him too. Side note.
No, that was a freebie. I'm just paying it forward.
That's funny.
Branch is paying me, so.
Yeah, go ahead, Coach. What were you gonna say, Coach?
No, Gio. He was asking you a question. That's what I was saying. I was only saying something because I was waiting for you to come back. But Branch had asked you a question, and we were anticipating. I don't remember what the question was. I do remember it, but I think Branch could probably repeat it if you didn't hear it.
You can repeat it, dude. I'm smoking a cigarette right now, so.
He's smoking.
Okay. Yeah, I'm on my phone. I'm on my phone, and I think it did drop out a little bit. Like it's been going in and out a little bit because I'm on my phone right now.
All right, so Gio.
So
Gio, the question is this, right? Assuming that it is the ether causing the Cavendish to do what it does and the pendulums to do what they do, if you had an experiment set up where you basically had the Cavendish running side by side a pendulum, and you do this in 3 different places, in northern hemisphere, southern hemisphere, and on the equator, why would the Cavendish experiments all show identical results, but the pendulums on the northern hemisphere they'll rotate clockwise, on the equator they won't rotate at all, and in the southern hemisphere they'll rotate anti-clockwise? Why would the ether be causing that type of behavior?
Sorry, you may have to repeat that one more time. Sorry, one more time.
Don't worry about it, dude. It's all good.
No, I,
So you should. It's
no, I,
it's
no,
very
it's for real.
simple.
No, just what you're talking
He
about
was
the
just
star
wondering.
rotations, or
No. He was wondering if you were to conduct a test where you did the Cavendish and Foucault's pendulum kind of together in 3 different locations, one north of the hemispheres, southern hemisphere, and also at the equator. And at all 3 locations, they behave the way that we predicted they'd behave. That means that the Cavendish worked correctly in all 3 places consistently. North of the equator, it spun or it precessed clockwise. The equator didn't precess at all, and the southern hemisphere precessed. And so all these things
yeah,
occur.
I got you.
He was saying that in your idea of the ether, because it was such a good idea, it was a great idea. But how would you say the ether is making this happen?
Yeah, I got you for sure. Yeah, so the equator is the dielectric inertial plane of the magnetic field on that vector. So like the equator is the midpoint between, like, okay, like if you imagine like a toroid and then you have a plane in the middle of it, that plane in the middle of it, that's the dielectric inertial plane. So that's the middle point of that field. So that's more of like that kind of structure. But if you imagine in terms of more of a magnetic structure coming out from the center, more like a dartboard, then the equator is the midpoint, which it's the point at which the polarity switches. So when I'm saying that the equator is the dielectric inertial plane version of the toroidal field. So the actual equator is that midpoint, which is why you get different readings in the north, on the equator in the south. It's not because the Earth's a globe and because it's spinning. It's because of the actual magnetic field and the way that the equator is the midpoint, which of course, like the equinox, you know, the way the sun works and the moon, it's literally the midpoint of all of the sun, the moon, and the wandering stars as well. So there's something unique about it. But that's why it's because there's it's the polarity shift. So it's the midpoint.
But then, okay, so that explains why the pendulums work differently. But then shouldn't the 3 Cavendish experiments have different results?
Well, the thing about quote unquote Cavendish in general is that generally there's a lot of different readings that are picked up and they end up just taking an average of them. So kind of like Riggs was saying before, there's not a single specific attractive value. There's a range of values that fluctuate, and then what they do is just claim an average. So yeah, so they're not actually getting one consistent reading. So if you were to do it at different areas, you could get slightly different results, which they do.
Good answer, man.
They should be